Hi, and welcome back to our flipped chemistry classroom. We're continuing our conversation about solutions today. So we focused on solution concentration and different ways of expressing solution concentration in our last lesson. And today we're going to use that as one more tool in stoichiometry. So we've done a little bit with molarity in stoichiometry before, but we're just coming back to revisit and hopefully just have a nice easy time with a little bit of stoichiometry. So just a quick review, quick reminder of our stoichiometry strategy is that we're always starting with some unit of either our reactant or our products. So in the past, we've usually started with mass, sometimes atoms, sometimes volume of a gas. In solutions, we're going to be starting with a volume of a solution. And so we know that anytime we do stoichiometry, we have to convert to moles. And so if we have mass, we know that we're going to do that by using molar mass. When we have the volume of a solution, remember this is very different from the volume of a gas. So the volume of a solution, we're going to use molarity to convert from liters to moles. And then just like any other stoichiometry problem, we're going to use our mole to mole ratio from our balanced chemical equation to go from moles of one substance to moles of another substance. And then, depending on what the question asks, we might be using molar mass to go back to mass of our new substance, or we might be using molarity again to get to a volume of a different solution. And so, same process as we've been doing with stoichiometry, we're just adding in a new conversion factor. So let's take a look at a sample problem, and this problem asks us how many grams of solid calcium hydroxide are required to react with 350 milliliters of 0.40 molar hydrochloric acid. So just like with any of our stoichiometry problems, the first thing that we're going to do is identify the given. And our given is going to be, in this case, the 0.40 molar HCl, 0.40 molar, oops, that's not our given, that's our conversion factor. Our given, let's try this again, is our 350 milliliters. Okay. And the unknown, the thing we're being asked to find, is grams of solid calcium hydroxide. So the unknown is grams of solid calcium hydroxide. So we need a balanced chemical equation, as with any other stoichiometry problem. So we have hydrochloric acid reacting with calcium hydroxide to form calcium chloride, which we know is solid, and we'll slide this over, water, which we know is in the liquid state. So I take a look, I have one hydrogen there, two hydrogens here, so 3, and I only have 2 here. But let's leave the hydrogen for the end of the problem. I see 2 calciums here, or chlorines here, and only 1 on this side. So I'm going to come back and put a 2 in front of the HCl. Now that gives me 2 hydrogens plus 2 hydrogens gives me 4 hydrogens. So I'm going to put a 2 in front of water. That gives me 4 hydrogens and 2 oxygens. 2 oxygens on this side. So hydrogens, oxygens, and chlorines are all balanced. I have 1 calcium and 1 calcium, so now my reaction is balanced. So I've balanced my chemical equation. I've identified the given and the unknown. One particular step that we're going to have to take in a solution stoichiometry problem is that if our given, as it is here, is in milliliters, we're going to need to convert that to liters because molarity is moles per liter. So 350 milliliters is equal to 0.35 liters. So I'm going to start with my given, 0.35 liters of hydrochloric acid. And I'm going to use molarity as a conversion factor because remember that molarity means moles per liter. So if I have 0.40 molar hydrochloric acid, that means I have 0.40 moles of hydrochloric acid per liter of hydrochloric acid solution. So I'm going to say 0.40 moles of HCl for every 1 liter of HCl solution, which we can just write HCl. And now we have gotten to moles of hydrochloric acid. Now we want to get to moles of unknown, which is our calcium hydroxide. And looking at my balanced chemical equation here, I can see that I have 2 moles of hydrochloric acid for every 1 mole of calcium hydroxide. And for every 1 mole of calcium hydroxide, we have 74.10, whoops, let's try and slide this way, grams of calcium hydroxide. And so now my liters of hydrochloric acid have canceled out. My moles of hydrochloric acid have canceled out. My moles of calcium hydroxide have canceled out, and I'm left with grams of calcium hydroxide. And so that's going to give me, I have only 2 significant figures, so that's going to give me 5.2 grams of calcium hydroxide. And that would be our final answer. Okay, let's do one more example just so you guys can see, but I think that stoichiometry is something that you're pretty solid in. We're just adding in one new conversion factor. So let's take a look and see what other fun examples we have here. Okay, let's do number 5 here. So it says how many liters of, we'll zoom in so you guys can see that. So we're going to do this one right here. How many liters of a 3.0 molar phosphoric acid solution are required to react with 4.5 grams of zinc? Okay, so we're looking to find how many liters of 3 molar phosphoric acid solution are required to react with 4.5 grams of zinc. So our given in this case, let's slide that up there and come back to here. Okay, so our given is 4.5 grams of zinc, 4.5 grams of zinc, and our unknown is liters of phosphoric acid solution. And we do have one more conversion factor that we need, and that's that we have 3.0 molar phosphoric acid. And remember that molar means moles per liter. So first thing, as always, is that we need our balanced chemical equation. So we're going to have our phosphoric acid, which is in solution, reacting with solid zinc to form zinc phosphate. That's going to be a solid, and hydrogen gas. Okay, so first thing I notice is that I have 2 phosphates on this side and only 1 over here. So I'm going to go ahead and put a 2 in front of my phosphoric acid. That's going to take care of the phosphate. Now I see 3 zincs on the product side, so I'm going to go ahead and put a 3 in front of the zinc on the reactant side. Now I see that I have 6 hydrogens and I only have 2 here, so I'm going to put a 3 in front of hydrogen. And that balances my chemical equation. So next thing we're going to do is set up our train track problem, our stoichiometry problem. And we're going to start with what we're given. Now notice that last time we started with a volume and went to mass. Now we're starting with mass and we're going to volume. Same process. So 4.5 grams of zinc. Now because we have grams, we're going to use molar mass as our conversion factor. So we look it up on the periodic table. We find that it's 65.38 grams of zinc for every 1 mole of zinc. And now I need to convert between moles of zinc and moles of phosphoric acid. So for every 3 moles of zinc, there are 2 moles of phosphoric acid. And now I need to get from moles of phosphoric acid to liters of phosphoric acid solution. And the conversion factor I have is 3.0 molar phosphoric acid. So remember, this means 3.0 moles of phosphoric acid for every 1 liter of phosphoric acid. And this is an exact number, this 1 liter, so that has infinite sig figs. So I have moles on the top, I want moles on the bottom, so we have to turn this over. So this is the one place that sometimes is a little bit of a challenge. So we're going to put 3.0 moles of phosphoric acid on the bottom and 1 liter of phosphoric acid solution on the top. And now we have 4.5 times 2 divided by 65.38 times 3 times 3. And that gives us 0.015 liters of phosphoric acid. So, same stoichiometry process, we've just added 1 more conversion factor. As always, I look forward to seeing you in class and answering any questions.